Okay, this is the last session of today's lecture. We are finishing at 1, guys. Okay, so we have already demonstrated that. We've come all the way up to here. Now everything down here is obvious. This proof is also very obvious. Now, this is what I've just demonstrated. You have n factorial, which is equivalent to this one here. So if you now have, if you expand this one here, guys, remember I've just demonstrated up here when I equated and we said that n factorial, I can just probably throw that back here. I told you that n factorial, that is after looking at the Laplace of t to the n in terms of gamma, and the Laplace of t to the n using the first definition we discussed in this, we have seen that this is n plus 1. Okay, this was n plus 1. Then I said if you wanted to just know n minus 1 factorial, n minus 1 factorial would simply give you minus 1 minus 1. This would be gamma of n. Okay. Now, what if we look at the would-be expansion of the factorial notation? Now we know that the expansion of the factorial notation, you have done this even in, by the way, I forgot, there is also something you call you've looked at these things in elements of probability and statistics, that is EPS. You have looked at these in probability theory, and you have also looked at these in statistical inference. So you can see that I'm really overly repeating myself. The crammers should be defending their titles of cramming, given that they crammed in EPS, they crammed in probability theory, they crammed in statistical inference. But as you all know, the crammers usually suffer from short memory. They overbombard their small heads with cramming, and then the things disappear as faster than the way they entered. So that is the problem. But now when you look at the expansion of this would be n into n minus 1 factorial. I think you agree with me here. So it is n into n minus 1, or if you want to continue further, this would be n minus 1, n minus 2 factorial. So n alone, but we know that n minus 1 factorial, it is gamma. So if you call this one 1, this is 2. So if we substitute 2 in 3, it implies that what? It implies that n factorial alone is simply n into gamma n. That is this thing you see here. We are saying now that this one here, this thing is equivalent to this one here. So this is what we are playing with. Enough of this boring stuff. Now you can go ahead and do the obvious, guys. Now just play with all of these. You will deal with this. You did that with this. Here, even the Kurama is now sorted. He has understood, or she has understood. These are now for non-negative integers, the same story. You come, you do all of these things here. You bring back a t to the 7. This one, everything is just fun here. Good, good. Keep opening your pages. Now we go to Laplace operation rules. Let's stop bogging each other down with those obvious things. Let's look at the Laplace operation rules. What are these? So if we go into these, then the question is, what is it that we are going to deal with in terms of someone here? There is a comment in the chat where someone says, Doctor, you are lecturing those other course unit or the easy two. I am lecturing the easy two, but the easy two has what we call prerequisites. You go to the head of a math department, you ask for the curriculum. They'll tell you, for you to do this course, you must have had these prerequisites. If you don't have them, my friend, you have entered into a wrong course. You can go and you do others like number theory, and there is also biomath. If it is a core for you and you did not do this, then you are surely a misplaced student. If this is a core for you, then you must have done EPS, you must have done a probability theory. And if it is again a core for you, then statistical inference must have been part of you. At least 2 of those 3 you must have done. Otherwise, you are in a wrong group. The same applies to this one who says that there is this gentleman already, Mr. Mokondere, Prince Jude, that you did not study EPS or probability theory. Impossible. Okay, I was just checking the questions you had in the chat. They are all over. We have covered all of the questions there. Okay, guys, have fun. Right. Now we have Laplace operation rules. What are these? These ones, the rules are more of guiding principles. Is that okay? So there is nothing really much. By the way, guys, I insist whatever we are discussing should be on your fingertips. So I'm hoping you are following. You are more than fit now for a test of even 100% given what we have discussed. So what are the rules? The first one is linearity. You have the Laplace of this function, which is AFT plus BGT. We are simply saying, we have already been applying this, by the way. You remember we are factoring things out. We've just done this in one of the previous examples where we threw a 2 out. We got a 2t, where was it? Somewhere here. And we threw this t 2 out and remained with the t. So this is now the f here. So these rules we are discussing, we have somehow used some of them already. Like this one, it has already been used. You can go ahead and you prove it. This is your f, then you use the definition. You don't have to waste time with this. This is obvious. Example 1, determine the Laplace of the following. Remember all of these here. If you have forgotten what we derived, I don't have to refer back, but you know, we looked at trigonometrical functions. So use what we did and we looked at examples here. And once you use trigonometrical functions, you simplify, you get the Laplace of that one. Okay. Here, same story. You have the Laplace of a series here, which is Cn t to the n, but we all know what t to the n is. So since it is Cn t to the n, we are saying if you have a series, the Laplace can actually go in. Just look at our L, the notation for L, it can go in inside the series. So that is L of that. And if that is the case, then you can take the Cn out, since you are going to look for the Laplace of t of n. Guys, be mindful of the notation in this example here. I'm hoping you are following me. This time everyone, not the grammars. So here we have L of the series. The L can go inside the series, so we can compute the Laplace of that. But remember, we talked about powers of t. So the Cn goes out and the L. Here we are applying the first rule. In here, we are already applying the first rule here, where we factored out. You can see a L of Ft. So we are already applying it here, but inside or within the set is Cn L of Tn. But you know what L of Tn is? The generic solution of that is n factorial over s of n factorial. And then you can do all of these ones. All of these ones, you can have fun. Well, okay, now we are on this one, change of scale. Those ones are finished. So if you go to change of scale, we can now look at that. So we can throw in some time here. One, if you talk of change of scale, here change of scale is usually necessary depending on the nature of the problem, of course, you have. You may find that rescaling the scale could either reduce on the cumbersomeness of the computation that one would have to endure. So it is necessary that you know how to change the scale. But the truth is, this change of scale we have been doing, there is nothing very interesting here. Why? Even in this example of gamma here, we have been changing the scale in here. And we ended up with our gamma function. Even before, you remember when we looked at the gt plus this part here, we had the change of scale in here. We changed the scales. So what is specific to this one here? Why I keep flipping back is just to alert you that the things I'm talking over now, they are not entirely new. You could even be tested on this one without even displaying it here, and you pass it because we have looked at it. Now I'm trying to talk to the Kuramas who may have crammed the other things wrongly. I am telling them even this one we have already finished. Why? So you have a change of scale. So LFT, you know this is FS. So if you have a GT, which is FAT, then we can compute this. So our L of GT here, by definition of Laplace, will be given by this. But remember, GT is F of AT. That is this F of AT to that one. Then we rate U equal to that. We substitute and we change. If this is the case, what will be T? From this, you definitely know that your T here will simply be a U over A. And you can see the 1 over A is up this one. So since the AT is U, what was F of AT? It is FU. You have that. Here you had the ST, but the T is U over A. You end up with this one here. Look at that there. I'll just throw emphasis on this one here. Remember our definition, guys. We have L, F of T, which is the integral from 0 to infinity. This is E minus ST. And this is, of course, the function you are looking at. And this is dt. But remember, this is F S. This one we have been looking at this since we started. So I'm trying to associate this with this part here. I'm trying to link this with this. Now here it is minus ST, but now what was the minus ST here is actually the minus, it is now the minus S over A. I'm hoping I'm clear, guys, here. So here we would refer to this as f of s. So since this cu is now s over a, it is now 1 over a. So the whole of this integral by definition is fs. So instead of this being fs, since we have rescaled, this is s over a, this becomes s over a. Okay. I think that is now very obvious. So if it means that if I have a certain GT, is that okay? If I have a certain, so if this is 2T, my GT is f of 8T, but that whole thing is 2T, then I simply have 1 over 2, then f of s over 2. Then I look for f of s over 2, which will have come from this integral. All right. Can I hear a yes in the chat room if you guys are hearing me? Can you hear me, guys? Have you abandoned the course? Someone says, you know, this command Lubega Po, I think is simply being stubborn. If you can't hear me, what are you doing online? Eh? Okay, I will go with Esau. There is Betty Kukundwakwe and Mr. Serunjoji. Oh, sorry, this is Madame Serunjoji Winnie. They can hear me. I can do without this Kurama Lubega Po. Kuramas always negate the answers. You know, being a Kurama is really bad. Eh? And some of these Kuramas may miss going to heaven. Where they should say yes, they insist on negating no. Where they should understand, they negate the understanding and they choose Kuraming. Eh? I hope you still remember negations from foundations of math. So, Lubega, I insist you can hear me. Eh? So don't just say you can't hear me. All right. Okay, so we can now go ahead, since even Rubega himself, he knows he can hear me, but he's pretending not to hear. Right. Yeah, that is basically it. We can look at another one here. So if it is ft, which is that, you now have this one here, f of t, which is that. Of course, we say a greater than 0. We have to be mindful of the definition being consistent with what we are doing. Now here, we don't even have to waste time. What if it is t over b? This is obvious. We come back here. Remember, this one here, we had the 8t. Now, instead of a, so it's like we are now taking the reciprocal of this one here. I don't know whether we are together here. Let me just explain it this way. Where is my writer? There you go. Guys, we had the f. This was f of 8t. That's what we had. So since it was f of 8t, we ended up with, from f of 8t, we ended up with this one here. Is that okay? So since we have ended up with this one here, then the question now is the A is now 1 over B. The A is now 1 over B. I don't know whether we are together, because now what we are looking at is from here. If you look at this one here, it is L. We are now looking at F into brackets 1 over B T. Hopefully we are together, which is just F over T over B. Hopefully we are together, guys. So this one, I don't even have to waste time. So it's like I am already operating here. Maybe I change the color so that people follow me clearly. So I am in the black now. All right. So since I am in the black, I replace A with 1 over B. If I replace A with 1 over B, I have T over B. Then what do I have here? This was 1 over A. What is this? But the A is 1 over B. So I have 1 divided by 1 over B, which is equivalent to what? Which is equivalent to B. I hope I am clear. So my 1 over A simply becomes a B. And here, since it was S over A, I have demonstrated that 1 over A is 1 divided by, the A is 1 over B. You change the reciprocal here, it becomes times, which is B, which is this one here. That one is finished. Good. Okay. Since that one is finished, we have cleared that one as well. We can go ahead. Now, we have this. Okay, we have already demonstrated this. Now we can look at some examples. How does this help? This helps, and I told you, please try to have these at your fingertips. So, number 1, if I have ft, which is s over s squared plus 9, then from this, I can infer L of ft, rather f, but now this was t. Now we have a coefficient. The coefficient here is 1. I had a coefficient of 1 here. In this one, I have a coefficient of 1. There is a coefficient of 1 there. Now, instead of a coefficient of 1, we have a coefficient of 5 here. So if f of t is s over s squared plus 9, now it is f of 5t. Since I already know this one here, I don't have to start from the beginning. I can now use my second property, this one here. Not this one, but rather the first one. Clear. Not clear, but rather, yes. So I can now use my change of scale, that one there. So what is this change of scale? Remember, I already have fs. So since I already know that this is s squared, s over s squared plus 9, my L of f 5t, it means it is 1 over 5 f of s over 5. But remember this one here, guys, is the same as f s. So what is this fs? Now, according to this one here, now initially it was fs, but it is now becoming f. It is now becoming f of s over 5. So I only have to have this f here, and I divide by 5. But this time, there is a coefficient of 1 over 5 outside. So that is why I have 1 over 5. The fs, which comes from f of L of ft, which is s over s squared plus 9, is already given here. So from this, it means I just have to divide each of these over 2, the s's. That is rather over 5. That is the s over 5 squared. And here you do the needful in terms of expanding. And when you expand, you end up with this as the final answer. That one is finished. Good. We can proceed. I'm just applying some of the concepts we've discussed for change of scale, and everything comes out directly. Okay, that one was that. Then here you can look at a combination of the two. Here we are still using the change of scale. So if you use again the change of scale on this one here, same story. What do we have? here we have been given L. Now, guys, it's like saying given L, T sine T is equal to this. Find this one here. Is that okay? Maybe I can just pause for you the question for you to get it well. I can write here. Let me put it. I can write it here, and I say given. This is given. That is L. Okay. This is L, and what do you have there? This is T. This is T sine T. Given that L, which is T sine T, this is equal to, okay? This is equal to what? This is equal to 2s. The whole of this is over. This is over, that is s squared. This is s squared. That is s squared. Then this is plus 1. And then the whole thing is squared. Okay? So given that LT is this, comma, find, we want now to find the Laplace, okay, of, we want to find the Laplace of T, that is sine 3t. And this is a full stop. I think we are together there. So that is basically what I am saying. That if you had wanted to have this, I'm looking for a clear page. Okay, so we are saying, given that L, the Laplace of T sine T is 2s over s squared plus 1, the whole thing is squared, then find the Laplace of T sine 3t. That is what we have here. Okay, since we have that right there, this is what we have, then we start. So our question is here. Given this, comma, find that one. That is why we are saying compute this. So we already know what T sine T is. It is 2s over s squared plus 1, that is squared. But remember, we already know our change of scale. We know that if you have a 3t here, is that okay? If you have a 3t, but remember that t here doesn't have the 3, so we have to be a little bit logical when we are doing this. The other one was ft, and we looked at the other one we had in the definition was it was g. We had g of t, which was f of a t. I think you remember that. So, but in here, we are looking for t sine 3t, but what we have here is t sine t. So for the sine 3t, this one would be okay. Rather, the t sine t would be okay, but now this t doesn't have the 3. Remember, the definition here is simply t sine t. But here we are looking for t sine 3t. So how do we go about this? Since we know that t sine 3t, we are using now the first rule. Remember the first rule, you can factor out. We had a rule which says that if you have L of a t, this can simply be, okay, f of t. You can have a out, then L of t. That is what we are doing here. So how should we ensure that we have something like this? Remember, this is what we are looking for here. So from our definition, we are looking for t sine 3t. So what is the equivalence of this? The equivalence of this is an identity. I have 1 over 3 times 3. Sure, I know that this 3 will cancel with that 3. So this is basically the same as this. That's why I'm choosing to use the word identity, that this is exactly the same as this. But this identity here will help us link or associate this new identity with this definition here. So in that case, what do we have? If I remove that, so I have t sine 3t, but my t sine 3t, this t can be written as 1 over 3, then 3t. What I'm trying to do is to associate this with what we have, because we are looking for t3t, so that I bring in my change of scale that we discussed earlier. Okay, so given that this is the case, then what do I have to do? I know that the whole of this now, the whole of this, just look at the red, guys. That red, the one I have circled. Since I have f of t, think of it, if I have f of t, which is t sine t, then it means if I have f, because now this is 3t, it means my t becomes 3t. This would be 3t, and this is sine 3t. This is sine 3t. That is what I have there. So to deal with this now, because this is where our change of scale comes in. So instead of, since I have this, I have generated, I've brought in this identity here. I have ended up with 1 over 3 now. The 1 over 3 is the term out. Then the 3t sine 3t, I've chosen to call it f3t, which is this one here. And if it is f3t, we are again using the properties. Remember, we discussed the properties up there. I can now take the 1 over 3 out. That is the 1 over 3 out. This is L f of 3t. But from our change of scale, we already know that if it is f of a t, it is 1 over a f of s over a. So the L, this L here is the term here in red. This one is what we have discussed. The L here. So we are going to simply say that our A is just a 3. And that is why we substitute. The 1 over 3 is this. That is the 1 over 3, 1 over 3. But remember, we already have the T, ST. So since we know FS, now be mindful that this whole thing here now, I will label it in black. This here. Please look at that. This here is our this is our FS. Hopefully we are clear there. So if this is FS, it means now for fs over 3, we just divide the s's here over 3. That's why we have now, there is this a third here, guys. Don't mess up the thirds. The a third you see out here came from the identity. That one comes from the identity here. Then the other a third that you see here comes from the change of scale. That is the 1 over 3, fs over 3. Then we have our 1 over 3. This is 2 Remember, there is a 2 here. So this S over 3, then this S over 3, the whole thing is squared. That is what we have there. Right. And now, if we go ahead, you can see that what remains here is a simplification. You are the stars in these things. So if you simplify this, that simplification will simply give you this one as the final answer. Right. We can go ahead. Now, the shifting we have, this is another beautiful thing. These ones we have also already discussed them. Everything we are discussing here, we are just formalizing what we have been discussing, guys. So the shifty property, you can shift it to the left, you can shift it to the right. You remember I told you when it comes to this, we'll talk about these shifts. And remember, we have already been looking at what we call the step functions, u of t minus a. We've looked at u of t minus 5. Remember, we have been discussing these things. You remember when we introduced the step functions. So it is L. Now, what is the L of this one? Remember, I told you you could have it as a 1 here. Then you could have it as a t. These things we have already discussed. So in here, we are just formalizing what we have been teaching, rather what we have been discussing. And really, I don't really have to discuss this one, sincerely speaking. I'll just be repeating myself with really the obvious that we have discussed. Because you see, we deduce that you have this one here. But remember, we have already discussed that if you have L, I think you guys, you still remember what we have discussed, that if you have L, this is U of T, this is minus A, this is of GT. Is that okay? We discussed this already. We have even looked at it today. We said this is E of minus S, A, this is the Laplace of G of T plus A. This is what I am saying, that I don't really have to repeat the obvious here. But the Kuramas, because they Kurammed, these things, if they do not even make a sense, the Kurama still wants me to again spoon feed him or her. This is the same thing. Now remember, here it was T minus A, G of T. So what is happening here? Of course, what is happening here is obvious. Here you have E to the minus SC, which was our A. So E minus SA. Here it was A because we are using A here, but this is minus C, which is this is minus C. So instead of C, we have A. But remember, for us, we moved, guys, if you remember, we moved from a GT. Remember when we discussed this? So this GT here, what you call GT here, this could be a 1 here, or what you call your GT, the L